Welcome to yet another installment of the quarantine set of videos introducing certain key topics in later stages AP chemistry. By this point, hopefully you've watched the video I linked to where Tyler DeWitt, I think, does a pretty good job, especially with some cool ways that he's layering text and diagrams and stuff on top of whiteboards, whatever, his introduction to electrochemistry. So I just wanted to run through a couple of things maybe that I should reinforce or that he omitted that I think should be included. A couple of things to reinforce. Again, he kind of states it at the beginning, the idea of what electrochemistry is. We're simply using the natural ability, the natural pull of some elements for electrons to generate a flow of electricity. And what is electricity? Simply but a flow of electrons. So electricity is simply a flow of electrons from one place to another. And that idea of electrons flowing from one place to another, we use the term current, which we'll talk more about in a couple days. Current is simply the measure of how many electrons are flowing from one place to another. Imagine a river, stronger current indicates more water flowing. So for us, more current, electrically speaking, means more electrons flowing. So the idea simply is that some compounds, some elements, some ions are just a lot better at pulling electrons than others are. And we have a sense of that already because it fairly well parallels electronegativity. So fluorine, for instance, is supremely good at taking electrons, and the alkali metals are very bad at taking electrons. And so you create a chart essentially that predicts that ability, but it's simply easier way maybe to do it is simply to mix elements together and see whether the electrons go from one element to another or vice versa. Really, there should be no elements that actually are tied. There should always be one element that is better than the other, whether it's slightly or greatly better than the other. There should always be one element that's better than another. So the key concept then is if I know that electrons flow naturally from one element or ion to another, the idea behind using that to make electricity is to separate those two things. So if electrons simply go straight from zinc to copper 2+, as he uses it in his diagram, and we'll talk more about today, there's no flow of electricity there because the electrons go directly from one element to another. So the key idea to generate electricity is to separate the two things so that actually we can harness the flow of electrons as it travels along a wire between the zinc and the copper 2+. A couple of things just as sort of a background on this. We call them Voltaic cells because of the Italian scientist Alessandro Volta. Tyler also uses the term galvanic cells. Galvanic cells also named for an Italian scientist named Luigi Galvani. Galvani did sort of crazy experiments on frogs, and if he had recently sort of killed a frog for experimentation, he found that when he was going to dissect it, if he used metals to pin the frog's legs down and a different metal to try to start dissecting it, the frog's legs would spasm when he did the dissection. And so he realized that there was some form of what he called animal electricity, that the animal was capable of generating electricity even though it was recently deceased. It still had this sort of life force in it. Volta took issue with the idea that it had to come from living things, and he created what are called Voltaic Piles, which are just sort of lumps of things like copper and zinc, and they can conduct electricity through these inanimate objects, kind of showing that an animal was not necessary to have it. However, as you probably know or should know, we are, as living creatures, very much tied to electricity. So our muscles, our nerves all function through electrical methods of building up charge inside and outside of cells, and then using that buildup of charge inside or outside of cells to generate a flow of charge. So we're generating electricity. And in fact, the idea of Frankenstein, the concept of kind of using that was because Mary Shelley was sitting in on some lectures given by scientists at the time, including Volta and others, and she sort of got the idea that you could use this sort of animal electricity as life force, perhaps to generate or create or reestablish life, which is not actually inaccurate in a lot of ways. If you think about what we do when someone has a heart attack, we're using electricity to restart their heart. So let me just kind of go through a little bit of I think maybe what Tyler does a pretty good job of, but glosses over a little bit in terms of actually discussing what a voltaic cell is and how to do it. He actually leaves out a very key part of a voltaic cell that I think should be mentioned in there. We're going to talk at least first today about in their standard form. Standard simply means that all solutions, if it's aqueous, things are 1 molar. If it's a gas, they're at 1 atm. And everything is at 25 Celsius or 298 Kelvin. We will discuss a little bit about how to modify that so that you can actually have different conditions to enhance electricity if that's what you so desire. So this will look a little bit like the diagram that he uses. So we usually have one container here, another container here. In his container, he used a bar of zinc, which I would certainly agree with using. This is classically known as the Daniele Cell, after a British scientist who sort of made it very famous. It was actually a very important cell. So that's just something to know. It's sort of the classic example that we use. And to keep it standard, we have our bar of zinc in a solution of 1 molar zinc 2+ ions. And there's other ions in here like chloride or nitrate or something, but we're not really too worried about those. On the other side of the container, we have a bar of copper in a bath of 1 molar copper 2+ ions. And that keeps it standardized. Now, in a real battery these days, of course, we don't keep things standardized to 1 molar, and you don't have to use the same solution as you do of the metal. You can mix and match to create all sorts of benefits from a battery standpoint. So stability, long life, higher voltage, etc. We'll talk a little bit about that in tomorrow's video. So if we connect these two things with a wire, I'll make the wire nice and thin here. The idea then is simply that electrons are going to naturally flow from the zinc to the copper 2+, as he sort of went through. The inherent ability of copper to gain electrons compared to zinc is higher, and we'll talk more about that tomorrow as well. There's a chart that sort of people have generated over the years that has the table of all those things. We've talked about it briefly earlier in the year, that shows all the elements kind of stacked up compared to each other. And because those two things are inherently one's better than the other, we would then know that the electrons are flowing from zinc to the copper. So that means we can track the flow of electrons leaving the bar of zinc and heading over to the copper 2+. They're actually being conducted through the bar of copper metal into the solution. So essentially wherever the solution touches the bar, which is conducting the electrons, we would see the reaction happening, not above the liquid level. An interesting thing too is, do not be under the idea that there's one electron that sort of magically is able to like make this miraculous journey from somewhere in here all the way along the wire. It doesn't work like that. If you remember the idea of the sea of electrons in metals, there's sort of freely floating electrons in a whole bunch of atoms. And so once there's a push or pull, depending on how you want to interpret it, that's felt, one electron starts to get pulled, let's say, from the zinc, and that pushes other electrons all the way along the wire, all the way into the bar of copper. And so at some endpoint, one electron gets pushed out of the bar into the bath of copper 2+ ions. So that's sort of how it would work. Now, one thing that Tyler left out that I would think is actually of critical importance is, if you think about this right now, this is not a circuit. It's not a loop. So that the instant you started this reaction, the zinc side would very quickly build up a positive charge, and electrons would have a very, 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 very nigh on impossible time leaving, because once it gets very positive, electrons which are negative can't leave. And on the copper side, as electrons arrived, a huge amount of negative charge would build up, and that would prevent future electrons from arriving because they would be repelled by the charge. And if you look at it right now, essentially what we have is not a circuit, because all we have, and I'll get rid of this in a second, all we have is this. Right? That's not a circuit. What we need is for something to flow back to the start. And so what is usually used in a diagram like this is what's called a salt bridge. And a salt bridge is not a bridge made of salt. It's a glass tube, and the glass tube is filled with a salt solution, so a solution of a conductive material that is non-reactive. So we call this the salt bridge. And the salt bridge, you might fill it with something like, potassium nitrate, so that it's made of ions, but those ions are themselves not going to get involved in the reaction because things like potassium and nitrate don't stick to anything in water. And what that allows to happen is, as negative charge, for instance, builds up on this side, so as negative charge kind of builds up on the copper side, that would be kind of a problem. As positive charge builds up here, that would be kind of a problem. So what ions, for instance, would be attracted to these positive charges? Well, the nitrates would. They'd be very attracted to the positive charge over here on the zinc side. So we would see nitrates flowing out of this tube. They are freely floating around in the solution, so you'd see nitrate ions being dumped out into the solution. So they would be attracted to the positive charge. What would be attracted to the negative charge over here on the copper side would be the potassium ions. So you would see a flow of potassium ions over to this side. If you think about it just from the negative particle viewpoint, so the nitrate ions, we said earlier you kind of have this flow of electrons, right, which are negative, flowing this way. So now we have negative ions flowing through the salt bridge this way. So that there's actually a complete circuit now of negative particles flowing along the wire and then through the salt bridge, so that you actually have a loop of negative charge going on. So now we actually have a circuit and the battery can actually operate. Without the salt bridge, the battery cannot operate. It won't work. So that's a very important consideration. I'm not really sure why it's not indicated a little bit more clearly in his video. So a couple of things for us to consider about what's going on here. Let me just give myself some more room. Okay, so what's happening here? So first of all, what's physically happening that we want to talk about? Well, the zinc is turning into zinc 2+, right? And as zinc turns into zinc 2+, then we actually would see this piece of zinc corroding. So it would actually be getting like eaten up. You'd see the metal, if you weighed it, would be getting lighter. And so holes would be opening up in the piece of zinc. It would be sort of rusting in a very aggressive sense. Over on the copper side, what we would see is that the piece of copper is actually getting thicker and thicker and thicker because the copper 2+ is being turned into solid copper. And so the bar of copper on the bottom part where it's under the liquid level is actually getting thicker and thicker as more solid copper is made. So that's one physical thing that you would certainly note. Physically, you might also notice that, again, the negative particles are traveling to the zinc side, the positive particles flowing to the copper side. You could certainly look at a conductivity meter and assess that. So some things that we should know about, as Tyler sort of mentioned, as negative particles flow to the zinc side, negative particles are called anions. So anions flow to the anode, right? Anions flow here. And that would make this side the cathode because cations flow to this side. So the K pluses are traveling to this side. So that's one thing. So the anode is a place where oxidation occurs. That's why Tyler used that example, which a lot of chemistry teachers use. NOx, red cat. So anox, anode, oxidation, red cat, reduction, cathode. So another way to remember is simply that both anode and oxidation begin with vowels, and cathode and reduction both begin with consonants. So that's something certainly to think about as well. Some other kind of considerations to begin to think about a little bit, which we'll talk more about tomorrow. Essentially, we could think about from Le Chatelier's principle perspective how to make this voltage higher or lower. Because if we have a lot, for instance, of copper 2+, well, that's a lot of reactant, and that will push the reaction more to the products. You can imagine that would make more volts. If we have a lot of zinc 2+, that unfortunately would cause the reaction to move back to the reactant side and reduces the voltage. So maybe we could reduce the amount of zinc 2+ to increase voltage. So that would be one thing to think about. There's also stoichiometric considerations here. How much zinc do you have? How much copper 2+ do you have? And we'll talk a little bit about this. The whole concept is that this reaction, when it goes from left to right, creates what are called volts, again, named after Volta, which volts are simply a measure essentially of how strongly the difference is between the pull of copper 2 plus and the pull of zinc. And the bigger that difference, the more likely it is for electrons to begin flowing from one side to the other. So volts are a measure of electric potential. What potential is there for electrons to travel from one side to the other? But I think that's enough for now. You got 2 videos that kind of go through this quite a bit. In tomorrow's video, we'll look more at some of the extensions to this idea, how to actually put some math behind it. And again, the Le Chatelier's principle perspective on how all this works. All right. Talk to you then. Bye.